So this is going to be looking at section 3.9. I want you guys to start with me with 3.9. Start on page 260. Okay, start on page 260. And so what you can see here is the title of this section is called Applications of the Derivative. Okay, so not that we're learning anything new with the derivative. We are now applying what we know about the derivative. Okay, it says we have learned that y equals f of x. Then the derivative can be interpreted as the rate of change of y with respect to x. In this section, we'll apply this interpretation to many different areas of study. Okay, so they walk through on page 261. Go to the top of page 261. It says, recall the basic idea of a rate of change. It is how x changes with respect to y. The difference quotient gives us the average rate of change. Average rate of change, y2 minus y1 over x2 minus x1. If we want a more accurate version of that, then we evaluate the limit as that change in x goes to 0, right? We bring the secant line to closer and closer and closer to the other one, so now it's a tangent line. This gives us the instantaneous rate of change. That is the derivative, okay? And so how is that useful? If you look, you've got a block, a little blue block on page 261. You see in the middle of page 261? Okay, it says in physics, if s of t is the position function of a particle, then the change in s over the change in t represents the average velocity. The function, ds dt, is the instantaneous velocity of the particle, the rate of change of position with respect to time. The instantaneous rate of change of velocity with respect to time is acceleration. Surely we know this by now, right? Okay. These formulas and notation were introduced earlier. However, using the many differentiation rules we've learned, we are able to solve problems involving particle motion more easily. So there is a huge application to physics. We've seen that. Particle motion, projectile motion, falling objects. Okay, you can calculate their acceleration, velocity, all of the stuff. If you go on to page 264. 264. This deals with density of a rod. Okay, the mass of a rod or a piece of wire is homogeneous. Then its linear density is uniform and defined as mass per length. This is still physics. Later on this school year, we'll go through finding moments of inertia of rods that are spinning. We'll find moments of inertia of wheels, moments of inertia of discs, all kinds of stuff like this. So we'll do plenty of this one in physics later on. If you're not also in physics, count yourself lucky. We don't have to do that for you guys. Okay. Example 3, electrical current. So this is more of the second half of your calculus-based physics. This will be third semester in college, right? This is the class right now that Ben's taking. This is electricity and magnetism, example 3. So you could find the current that's moving through a specific, what is this? A wire. Okay, so you could calculate the change in electric current over time. That's, again, the derivative, change in current per time. Okay. If we keep going, there's a chemical reaction. Chemistry. So we see applications in chemistry here. You've got reactants, you've got products, you've got concentration. Instantaneous rate of reaction would be how quickly the thing is reacting with respect to time. Can you see that? The derivative in chemistry. Keep going. Compressibility. So that's going to deal with volume and pressure. Thermodynamics, a lot more chemistry there. Okay. If you look at biology, you could look at the growth rate. Imagine putting some bacteria in a petri dish and trying to decide how fast is it growing. So not what is the growth at a certain time, that would be input-output, but what's the rate of change of growth? What's the derivative? Okay. Blood flow, that's biology. That's talking about like blood flow throughout the veins, laminar flow. So how is the blood flowing? You could imagine if there was a bunch of plaque buildup, the blood wouldn't flow as quickly. So you could examine the rate of change of blood flow and tell a whole lot about the person's health, their blood pressure, lots of things like that. Okay, keep going. You see an application in economics. Example 8, that's marginal cost. So it says, suppose C of X is the total cost of the company. And then what do we want to know? The rate of change of cost. So production. Rate of change of cost with respect to time. Okay. If it's costing a whole lot more to produce my items, then maybe I want to hire more people. Maybe I want to downsize my company. I can't keep up with the production cost. Okay. So if you're a businessman, there's a whole lot of application of derivatives here. You can read rates of change within your company. Okay. Other scientists, there's all kinds of applications. We could work through every single example, right? But the chances are of you being tested over one of these particular exact examples on the AP test, I can't predict that. I have no idea. Your job is to understand what the derivative means as a rate of change and be able to apply that to any question that they ask you. Okay? So I don't think it's necessary to sit here in this particular section and deep dive into every single example, because that's not going to help you in the long run. That's not going to mean that you could do the example that they have you do or the problem they have you do on the AP test just because you worked this specific one in this classroom. Does that make sense? So instead, I want to read at the very bottom of page 269. It says, a single idea with many interpretations. A single idea with many interpretations. So at the bottom it says velocity, density, current, power, temperature gradient in physics, rate of reaction, compressibility in chemistry, rate of growth, blood velocity gradient in biology, marginal cost, marginal profit in economics, rate of heat flow in geology, rate of improvement of performance in psychology, rate of spread of a rumor in sociology. These are all specific cases of a single mathematical concept, the derivative, the rate of change. This is an illustration of the fact that part of the power of mathematics lies in its abstractness. A single abstract mathematical concept, such as the derivative, can have different interpretations in each of the sciences. When we develop the properties of a mathematical concept, we can then apply these results to all of the sciences. This is much more efficient than developing properties for special concepts in each separate science. Okay, so we've got this overarching idea of the derivative as a rate of change. Now you can take it and apply it to all different facets of science. The French mathematician Joseph Fourier put it succinctly: mathematics compares the most diverse phenomena and discovers the secret analogies that unite them. So in each one of these different situations, we could see the usefulness of the derivative. Okay? I'm going to trust that you guys don't need us to walk through each one of those examples. You do have a homework assignment over this section. I think it's good practice. I think applying is good. I don't think the examples are going to help you with your homework. Okay? So you do have a homework assignment here. It is 3.9. It's not a lot. If you get pretty decent at it and you decide I'm kind of done with this, then don't worry about it. Okay? 3.9, you've got number 5, 6, 9, 11, 13, 15, 19, 29, and 31. Okay? Again, these are just application questions. Look in your syllabus. Oh, yeah. Okay, so does that kind of answer the question, like why we're not going through this section one step at a time? If you do want some practice here, you could spend some time going through your homework problems. I did want to work the particle motion question in example 1. The reason I wanted to work it is because that's what you're testing over in physics. So I thought it might be good to look at it in a calculus point of view and see what happens here. Cool? Yeah. Any questions on that? Everybody okay? No? Okay, so we're not going to get very far here. We've got maybe 15 minutes, 14 minutes until the bell rings. So we'll get a little ways. Obviously, this example 1 has questions A through I. So, like I said, we could spend a couple of days here. We'll try to zoom as quickly as we can through this part, but I'm not super worried about it. Okay, so it says a particle moves along a straight line. So now this is not projectile motion. This is like straight line, one-dimensional kinematics. Okay, so either it's a falling object or it's something that's going back and forth on an x-axis like this. Okay. It says the position of the particle is given by S of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s in meters. Okay. Find the velocity at any time t. So for part A, find the velocity at any time t. So how do I find velocity? Our position function here is s of t equals t cubed minus 6t squared plus 9t. So part A says find the velocity at any time. So take its derivative. 3t squared minus 12t plus 9. Okay, at any time, we're just going to leave it t. Okay, I think they're going to ask us more about that moving forward. All right, so letter B. Letter B on this one question that's going to last half our lives. What does it say for B? Find the velocity at time t equals 2 and t equals 4. Yeah, so for part B, we're finding v of 2 and v of 4. Okay, so that means for t, I'm going to plug a 2. We got, what, 12 minus 24 is negative 12 plus 9, negative 3 meters per second. Did they tell me units? Yep, where t is measured in seconds and s is measured in meters. Okay, v of 4. 48 minus 48 plus 9. 9 meters per second. Okay. Part C says find all times when the particle is at rest. Find all times when the particle is at rest. So talk to me about what you know about a particle being at rest. Its velocity is 0, right? If it is at rest, v of t equals 0. So we can set our v of t function 3t squared minus 12t plus 9 equal to 0. If I were going to try to solve this thing, I would factor out a GCF first. Because that would be, what is the velocity at time t equals 0? That's a different question. The question is, when is it at rest? Which means its velocity equals 0. Does that make sense? So 3, I pulled a 3. I've got t squared. I can divide that 3 off. That was a question in Algebra 2 yesterday. Where did the 3 go? You can divide it. 0 divided by 3 and it's gone. T squared minus 4t plus 3 equals 0. If my 3 is positive but my 4 is negative, then that means what? Both factors are negative. So t minus 1 and t minus 3. So the particle is at rest at t equals 1 and at t equals 3 seconds. So far, so good? Okay. So back here, we've done A and B and C. The question